Hey folks, we are having some major technical difficulties today, so I'm hopping on late on stream because my camera is not working again, um, and because I was putting together some stuff I actually did want to show on the stream, but I can't because the camera's not working. Um, so the chat box is not up and running. I am still totally willing to chat with you, so feel free to send me a message or anything. I have it open in OBS, so I can see it there. I just can't display it on the screen right now, just like with my camera, which I assure you is actually on, and the light is on. Um, but I know what the problem is. It's every time I like so my webcam is a Panasonic GH5, and it's hooked up to my desktop through an Elgato capture card. And I've noticed every time I unplug it on the camera side, it basically won't reconnect back to my desktop's capture card whenever I plug back in. At least I think that's what the problem is. It could actually be that it could actually be something else. Like I've been putting my computer to sleep, and I don't know if maybe putting it to sleep makes something not work with the capture card. Um, yeah, I should probably just shut off my computer instead of putting it to sleep. But you know, it's just for me, it's just easier to. Actually, I don't even know why. Anyway, let's rewind a bit, and I will show the things I wanted to show next time. I have to get started because I have a lot of stuff to do. Actually, I need to cook dinner, and also I got some take-home assignments for job interviews, and I kind of need to get those going. Um, so, if you are new to the stream, my name is Aaron. I am a data scientist, and I'm currently with the Centers for Medicare and Medicaid. So, I'm a government employee. Excuse me. Sorry, I'm a federal government employee working in data science. And, you know, I'm one of the original, yeah, this is probably fair to say, one of the original data science hires within my group. And yeah, things have been interesting, but as you can tell from me saying a couple minutes earlier that I got some take home assignments, like I am, of course, looking for something a little bit better, something that I find a little bit more technically minded, and that's why I've been interviewing. Um, and you know, just to see what's out there. Don't want to be surprised a couple years from now if I, you know, want something totally different and then I don't have any idea what the field is up to. And the reason why I'm doing these streams right now is that I am not focused on the right window. I am actually trying to review my stats knowledge. So I don't really do a lot of statistics, unfortunately, in my current role at Medicare, which is odd, right? So I wanted to go back and practice a bunch of stuff, and I found out that I was doing a lot of like applied machine learning and applied statistics stuff for my side projects. And sometimes I would look at the documentation for the code and just say like, oh, how do I know that this algorithm or this library I'm using or this function within this library can actually be applied here? Like, what is the underlying theory? So I tried to roll back and look at basic statistical theory to see what could actually be applicable. And super interesting. It was kind of odd and hard to find some of these like more intro online SAC courses that are free. So yeah, actually even paid when I went to go to Coursera and stuff, like they're basically all like applied statistics. So I've been doing these streams to try to force myself to study because it's so easy to not do that. And they've been working somewhat well, about an hour every 2 days, Tuesday, Thursday. Try to go for 2 hours, but you know, it doesn't always work out. So exciting things I've found the past couple days. There's actually a post in our data science about if you are on the job search, resources to actually look at to prepare you for doing data science interviews. So I'll also be looking at that. And today, oh yeah, and then I have these take-home things. I only have like a couple days to reply, so that's why I'm in kind of a time crunch. So yeah, today I will actually be looking at probably two classes. I usually do these at like 1.5, 2 times speed. I don't remember doing this more RVs class, and it's possible that I started it, and then YouTube, like, for some reason just finished out the status. But I'll be going through some of these today, mostly more RVs and QQ plots. If I've already done more RVs, I'll probably skip to start doing a little bit of multivariate probability. So unfortunately, because my camera's not working, I can't show you that I'm actually working, but trust me, I am actually taking these classes. So without further ado, I will hop into the first class. And, if there's anything you're studying, wow, I forgot to change the microphone output. Sorry, speaker output. If there's anything you're studying and you want an accountability buddy, just let me know in the chat. I'm curious to see what people are working on or trying to learn. This whole series was inspired by Tina Huang, who is a data scientist in some FANG company. Highly suggest that you check out her channel too. So I was going to put that in the chat, and that would show up on the left, and I forgot that there is not working chat today. So yeah, I will, I guess, to let you know that I am actually working, I guess I'll just, I don't know, put Spotify on and have like Streamlabs or the lo-fi chill beats or whatever streaming. Yeah, I'm super sorry that like I'm having so many technical issues. All right, stream beats. How could I add this onto here? I never figured this part out entirely. Oh gosh, okay. Alright, I will skip the having stream beats on, or Spotify on, because I remember looking this up and I never fixed it. So yeah, cool. Maybe if I try to figure out how to share Spotify, but it won't play the audio, and also try to share Spotify without revealing my friends, because that is technically a violation of personal information. Okay, cool. Probably would be a lot better if I didn't do this on stream, but whatever. I'm super sorry for that. It's very unprofessional streamer of me. Okay, I'm gonna hop in a class. So yeah, I will talk to y'all later. Feel free to message in the chat.
We are now going to start another section, this one with even more continuous random variables that often show up in applications in in various contexts. I mean, I would say that everyone, we are now discussing the ever famous, maybe too famous, sometimes infamous, not infamous, that's not a word, sometimes infamous normal distribution. We say that a random variable x follows the normal distribution, sometimes denoted like so, same deviation 15, like mate a distribution directly. So 110 and lambda is equal to 100. Your responsibility to fix it. Part of the way you fix it. All right, so that's it for this section, and I will see you in the next section when we talk about exponential random variables, which we've already talked about quite a bit. Hey everyone, we are next on to the exponential and gamma distributions. We're going to be talking some more about some special continuous random variables in statistics and probability.
So I found
we're going to start by talking about the exponential distribution, but we've already seen a lot of the exponential distribution. We've already done a lot of those calculations. I was using it as an example distribution. So let's kind of recall what we have seen so far over the previous videos. Let's say that x follows an exponential distribution.
Yeah.
With
all right. That's a 40-minute video. I'm not.
If this is the case, then the PDF for this random variable is going to be either 1 over mu e negative x over mu for x greater than or equal to 0, or it's going to be 0 otherwise. The CDF for an exponential distribution with mean parameter mu is going to be 1 minus e negative x over mu for x greater than or equal to 0, or 0 otherwise. The expected value of such a random variable is, of course, mu. Hold on. Is that button still refusing to work? All right, so this is still mu, and its variance is equal to mu. And we could say that our quantile function, eta of p, will be, what do we have? Negative mu ln 1 minus p if p is in the interval 0 to 1. It will be 0 if p equals 0, and it will be infinity if p equals 1. Which, of course, means that our quantile function isn't strictly a function, since infinity is not a number. But you get the idea of what it's trying to say. Like, if we could say that infinity was a number, then this is what it would be. All right, exponential random variables can be used to model waiting times, particularly when a process is memoryless. That is, the time remaining until the process terminates is independent of how long the process has currently taken. Or, so proposition 2, memoryless property. Let's suppose that t is following an exponential distribution with mean mu. Then the probability that t is greater than or equal to t plus t naught, given that t is greater than or equal to t naught, is the same as the probability that t is greater than or equal to t. What this is saying is that if you know that you've waited t naught, at least t naught seconds, for a process to terminate, you basically get to restart. And if you're wondering if it's going to take at least t more seconds, knowing that it's taken at least t naught seconds, or that t naught seconds have passed, tells you basically nothing about the distribution or when this process is going to terminate. Because this is basically, even if you'd started out, like right now, at this moment, t naught seconds have passed, and whether it's going to complete in t seconds is exactly the same as if t naught seconds ago you asked the same question. Okay, so let's prove this. The probability that t is greater than or equal to t plus t naught, given t is greater than or equal to t naught, that's going to be the probability of, so we have the intersection of the two events. So the intersection of t is greater than or equal to little t plus t naught. Are we running out of room? No, not quite. Intersected with the event that t is greater than or equal to t naught, divided by the probability that t is greater than or equal to t naught. Okay, and, stop doing that. All right, so this is, so in the denominator we have the probability that t is greater than or equal to t naught. And now let's examine the set that we wrote down in the numerator. What is the intersection of these two events going to be? So we require essentially either that, let's maybe create a number line that might, let's create a number line that might be somewhat revealing. Here is t naught, here is t plus t naught, and we need to be greater than or equal to, all right, so this thing is increasing. So we need to be greater than or equal to t plus t naught, so we need to be in the blue region, and we also need to be in the red region. We need to be in both of those regions. But clearly, if we're going to be in both of them, then we are going to be in the blue one, and the blue one is a subset of the red one, right? In other words, if you need to be both greater than or equal to t and t plus t naught, and also greater than or equal to t naught, since being greater than or equal to t plus t naught is the more restrictive condition, that is effectively the condition that takes over. So this is going to be the probability that t is greater than or equal to t plus t naught, divided by the probability that t is greater than or equal to t naught, and we can compute those probabilities. 1 minus the CDF is going to be, well, okay, we have kind of this simplifying fact that 1 minus f of x parameterized by mu is going to be e negative x over mu, assuming that x is appropriate. I'm going to let you see that yourself. I'm going to leave that as an exercise for you, but it's not at all hard to see that that's the case. So we have e negative 1 over mu, t plus t naught, divided by e negative 1 over mu, t naught. And the t naught in the numerator and the t naught in the denominator cancel out. So you're left with e negative 1 over mu t, which is what we want, which is equal to the probability that t is greater than or equal to t, which is what we wanted to show. All right, hence these random variables are memoryless. All right, so exponential random variables play an important part in Poisson processes. The time between subsequent jumps of a Poisson process with parameter alpha follows an exponential distribution with mean mu, which is equal to 1 over alpha. So let's work on an example. Your daughter's team scores on average 10 points per game. You model the points scored by her team in a game with a Poisson process, and t equals 1 is a whole game. Based on this, what is the expected time between jumps scored by your daughter's team? Okay, so for this, we could say, let's say that ti is, so let ti be the time between points I minus 1 and I for I greater than or equal to 1. Okay, so we can then say that for any I, the ti, which is going to be the time between a jump in the process, which corresponds to the soccer team scoring a point, is going to follow an exponential distribution with mean parameter 1 over 10. Okay, because the alpha parameter is a 10, I believe. Is that right? Yeah, that's right. So the alpha parameter is 10. So in this problem, so that means that the expected value of ti is going to be, well, 1 over 10. There we go. Next part. Suppose that by the start of the second half, your daughter's team has scored 3 points. Given this, what is the expected time when your daughter's team score is 4 points? Well, all right. So in this case, we're studying with T4. So we are asking what is the expected value of T4, knowing that that we have reached halftime. And that at halftime there are 3 points. Well, okay, in this situation, T4, so we know that T4 is following an exponential distribution with mean parameter 1 over 10. Thing though is, knowing this information, then T4 is going to be equal to, let's say, it's going to be equal in distribution to T1 plus 0.5 because of that memoryless property. So we know that it has been, that it's up to halftime, but after that, you're basically just adding 1/2 to an exponential random variable, because what we're saying essentially is that when we're saying that a random variable is memoryless, is that its distribution its conditional distribution, conditioning on the fact that it's been so long since the process has started, doesn't change. So that means, so that means that we can, I suppose we could say this. So that means that we can basically just add 1/2. I don't know. I don't want to say that. We could just add 1/2, and we will have accounted for the fact that it's after halftime. So then the expected value of T1 plus 0.5 is going to be 0.1 plus 0.5, which is equal to 0.6. So in other words, we expect the 4th point to be scored 6/10 of the way through the game. Okay. And here's some R code that's doing a lot of this stuff. This is just basically computing an expected value for when the rate parameter is 10 of a exponential random variable. So compute its expected value and so on. All right. So we've seen a lot of this stuff before already. So let's go ahead and move on. We're now going to talk about gamma random variables. And before we do that, we have to talk about the gamma function. So the gamma function, gamma alpha, is going to be gamma alpha, which is equal to the integral from 0 to infinity x alpha minus 1 e negative x dx for alpha greater than 0. And that's what it is. I don't get to write anything really simpler than that in general. There are special cases for which gamma alpha is known. For instance, it can be determined via integration by parts that gamma of alpha plus 1 is equal to alpha times gamma alpha, right? And furthermore, gamma of 1 is equal to 1. Now, the fact that gamma 1 equals 1 is pretty easy to see because you could, basically when you're doing this integration, you're only integrating the blue part. And if you're integrating only the blue part, that integral is going to be 1. You should know this by now because that's basically the PDF of an exponential distribution with mean parameter 1. You're integrating it over its over the support of that random variable. Like there's several different reasons now why that integral is going to be 1, but that's what you're going to end up with. So based off of these two facts, where this first fact, you can determine this using integration by parts. So this is found by integration by parts. So if you're planning on taking more advanced math classes, I would hope that you would take the time to go through the motions of integrating by parts to see that this relationship does in fact hold. All right. But once you have these two facts, you get to say that gamma of n plus 1 is equal to n factorial. If you're familiar with proofs, if maybe you've taken discrete mathematics, this can be proven via induction. So, but this is basically a consequence of that. So therefore, we get to say that the gamma function is the continuous analog of n factorial. Right. So n factorial was something that we were defining in terms of integers, but now we get to define it in terms of positive real numbers and not just the integers. So you get to move beyond what we had before. All right. Here's some other facts. It can be determined that gamma of 1/2 is equal to the square root of pi. And additionally, we have that gamma of 1 minus z times the gamma function at z is equal to pi over sine at pi z. Okay, I'm gonna have to put that in a better place. Okay, so gamma 1 minus z is equal to pi over sine pi z when z is not an integer. Remember that Blackboard bold z? That is referring to the integers. So for non-integer z, you have this relationship. And there are more. There are more identities for the gamma function. This is a well-studied function because it's appearing in many, many places. So we do know the value of the gamma function at certain alpha, but in general, we don't know what this is, and we are forced to just leave this formula, this integral as it is, and just say this is what it is, this is how we're defining it. If we want to compute this thing, we have to compute it numerically. Okay, so there is another function called the lower incomplete gamma function, which we're calling gamma alpha x, but this is a lowercase gamma rather than uppercase gamma. And the lower incomplete gamma function, gamma alpha x, hold on. Okay, all right, that is equal to the integral from 0 to x, t alpha minus 1, e negative t dt. And this yields what we call the obvious. This is basically there's an obvious relationship. If you were to take this upper end of the integral x and send it off to infinity, then you're going to get the full gamma function. So you end up with this relationship that the limit as x approaches infinity of the lower gamma function is going to equal gamma at alpha. So the full or complete gamma function at alpha. Okay. Once you have these functions, you can define the CDF and PDF of what's known as a gamma distribution, or a gamma random variable. All right? So this random variable is specified by two parameters, alpha and beta. These are known as the shape and the scale parameters, respectively. So this is a shape parameter, and this is a scale parameter. And our PDF for this random variable, so f of x, with parameters alpha and beta, is equal to 1 over gamma alpha, beta to the power alpha, x alpha minus 1, e negative x over beta for x greater than or equal to 0. If x is less than 0, then we're going to have 0 for our PDF, so I'm not even going to bother to write it. All right, the probability that x is less than or equal to some little x, which corresponds to the CDF of this random variable. So this is the CDF of this random variable. We have two parameters, alpha and beta. That is going to be, literally by definition, the integral from 0 to x, f of t alpha beta dt, if x is greater than or equal to 0. Otherwise, it's going to be 0. Which is equal to, furthermore, the incomplete gamma function evaluated at x over beta divided by the full gamma function if x is greater than or equal to 0. And it's 0 otherwise. Okay? All right. So if beta is equal to 1, then we were going to refer to the random variable with parameters gamma alpha 1 as the standard gamma distribution for that alpha. So there are different standard gamma distributions for different alphas, but yeah, you do get one standard gamma distribution. This is basically setting the scale parameter equal to 1. We do have a table in Devore's book, table 8.4, that's giving the values of the CDF of the standard gamma distribution for particular alpha and x. Since we are working largely on computers, though, I don't know how much attention we are actually going to pay to that fact. So the standard gamma distribution can be used to compute probabilities involving non-standard gamma distributions in the following way. Let's call, just for notation, x a gamma random variable, or an arbitrary gamma random variable. So it has a shape parameter alpha and scale parameter beta, and we will define a corresponding standard gamma random variable. So this random variable has shape parameter alpha and scale parameter 1. Then the probability that x is less than or equal to little x is equal to the probability that y is less than or equal to x divided by the shape parameter beta. So what that suggests is when tabulating quantities for computing CDFs for gamma random variables, you only need to do it for the standard gamma random variable. You only need to worry about the shape parameter and not the scale parameter. And if you look at table 8.4, that is what you'll see happening. All right. So the mean and variance of gamma random variables. For the mean, we get alpha times beta, and for the variance, we get alpha beta squared. Okay, example 17. In a paper by Husek et al., the amount of rain in millimeters in Istanbul is fitted. Does Istanbul have 2 L's or 1 L? I think that's a mistake. There should be 1 L, not two. Oh well. All right, so the amount of rain in Istanbul fitted to a gamma distribution. So they fitted the amount of rain in Istanbul to a gamma distribution, and the author estimated that the distribution of the amount of rain in April is R, and it can be modeled by a gamma random variable with shape parameter 0.436 and scale parameter 11.05. So based off of this, compute the mean and standard deviation of the April rainfall. So the mean is going to be, according to those formulas, 0.436 times 11.05, which is going to be 4.8178. The variance of our random variable is going to be 0.436 times 11.05 squared, which is equal to 53.23669. Finally, the standard deviation of our random variable is going to be the square root of the variance, which is approximately 7.296. Okay. So here's a curve of that random variable. This is what its PDF will look like. And I computed its mean. We have in R the shape parameter. This corresponds to alpha, and the scale parameter that corresponds to beta. So this is how we would compute its expected value. Here's how we compute its variance. This is probably looking a whole lot like what we've done before. I even computed the probability that in a year you get more than, let's see, is that annual again? No, just April. So the probability that in April you get more than 1 millimeter of rain. So you could compute that using the P gamma function. Notice I'm using lower tail equals false because I want the probability that the amount of rain exceeds a millimeter, and this is the probability that we end up with. So about a 60% chance. All right. Let xt be a Poisson process with rate parameter alpha. Let tk be the time until the process is equal to k. That is, tk is the smallest t such that xt is equal to k. So that means that xtk is equal to k. The distribution of tk is in fact known. The distribution of tk will be a gamma distribution with, let's see, so the shape parameter will be k, and the scale parameter will be 1 over alpha, if I remember correctly. Yes, that is correct. That is correct. That is how I've written things down. You kind of have, remember how I mentioned with the exponential random variable, there's some issues about the notation, and we might specify things in terms of the mean or in terms of the rate. The gamma distribution also has a similar issue, this similar conflict in notation. And that's why I had to think about it for a little bit if it would still, in fact, be 1 over alpha. But it is. And actually, it gets to the point which I make, not here, but here, that, in fact, there is a relationship between gamma random variables and exponential random variables. And, in fact, well, okay, you know what? We're already here. This is page 137 of the main lecture notes. So if x follows an exponential distribution with mean parameter mu, that's going to be true if and only if x is also following a gamma distribution with shape parameter 1 and scale parameter mu. And in fact, let's go back a little bit to let's go back up to the mean and variance that I wrote down for a gamma random variable, notice that we could think of, if we're talking about a Poisson process, the time until the kth occurrence of an event, well, we know that the times separating the occurrences of those events are exponential random variables. And let's suppose for a second that they are, well, okay, they're not just exponential, they're independent exponential, right? They're all independent of each other. So you could think of the time until the kth occurrence as the sum of k independent and also identically distributed exponential random variables. And in that case, you would have for your mean, the expected value of tk, you would have for that k 1 over alpha, which is k times the expected value of one of those independent exponentials. And for the variance, you would have k 1 over alpha squared, which is k times the variance of one of those. Intriguing fact. Okay. It looks like I've chosen some unfortunate notation, where in a previous example, I was using tk to mean the time separating jumps. But here I'm using tk as the time until the kth jump, and that's unfortunate. I apologize that I did that notation. It's not exactly easy to work with. So, it's easy to work with, but it's somewhat confusing that here when I write tk, that's not going to be the same tk that I was mentioning in the previous example. So I'll even just make a note of that to help you clarify. So not the same. So this is not the same tk as before. My apologies. Sorry about that. Anyway, tk. So what is the mean? So this is going to be the time until the kth jump, and that follows a gamma distribution with shape parameter k and scale parameter 1 over 10, because in this case the alpha parameter is 10. So in this case, if we're interested in the mean and standard deviation of the time until the team scores 5 points, the random variable in question is t5, which is following a gamma distribution with shape parameter 5 and scale parameter 1 over 10. Okay, so I want the expected value of t5, but this is the time until the team scores their 5th point. That's going to be, well, the shape parameter is 5 and the scale parameter is 1 over 10. So this is going to be 1/2, or halftime. So you expect the team to score their 5th point at halftime when they're on average scoring 10 points a game. Super intuitive. Now we need the variance of t5. So the variance of t5 is going to be 5 times 1 over 100, which is going to be 5 over 100, which is 1 over 20. So that means that the standard deviation of t5 is going to be the square root of 1 over 20, which is 1 over 2 times the square root of 5, for what it's worth. Or if you don't like roots in the denominator, if you're one of those people who actually cares about that sort of thing, this is the square root of 5 divided by 10. Whatever. I don't really care. Let's see. I suppose that that's a little bit easier to work with, because we could say, all right, what's the square root of 5? Well, the square root of 5, 2 squared is 4, and 3 squared is 9. So the square root of 5 is slightly larger than 2. So that means the standard deviation is going to be around 0.2, like maybe 0.23 or something. So on average, the time it takes to score that 5th point, it's going to be halftime, and within about like a third of the game and a 1/7 of the game. So you could think of it that way. All right, what is the probability that the time until her team scores 5 points is before halftime? So what is the probability that the time that her team scores 5 points is before halftime? Okay. So let's see. If we really wanted to work with standard gamma random variables, then we could say, all right, we got T5 following a gamma with shape parameter 5, scale parameter 1/10. The corresponding standard gamma would follow a gamma distribution with shape parameter 5 and scale parameter 1. So that would mean that this is equal to, so we could divide both sides by the scale parameter. So that would be, this is the probability then that 10 times T5, oops. So 10 times T5, which is the same as dividing by 1/10, is less than 5, which is equal to the probability that our standard gamma random variable is less than 5. Okay. Okay then, so if we wanted to use that, we now need to go to R. So we go to R and we say, all right, so the function in question is going to be p gamma. So we want to work with a standard gamma. So our input is going to be 5, and we do need to say that the shape is equal to 5. All right, so it says 0.5595, we'll say. So this is approximately 0.5595. Alternatively, though, we could have said, all right, we got the shape parameter and we got the scale parameter. So scale equals 10, but we're going to have to change the input. So then instead of being 5, it'll be 0.5. Uh-oh. Oh, right. The scale parameter is 1 divided by 10. There we go. That's the same number. That's better. Okay. Right. So here is the curve of this gamma random variable that we've been studying in this problem. We compute its mean, its variance, its standard deviation. So, oh yeah, my guess that it was about like 0.23 was pretty close. And then the probability that it's greater than 1 is what we give. All right. So we also have what I mentioned before, that exponential random variables are actually a specific case of a gamma random variable. So gamma random variables include exponential random variables. Additionally, there's another class of variable that we're going to talk about in this section called this chi-square distribution. So the chi-square distribution, such random variables are denoted like so. We say x follows the chi-square distribution with degrees of freedom parameter nu. Oh, maybe you remember me mentioning this idea of degrees of freedom way back in chapter 1 when talking about the sample variance. Well, there is a distribution that uses degrees of freedom as its parameter. Now, in this case, it turns out that a chi-square distribution is basically the same as a gamma distribution with shape parameter nu divided by 2 and scale parameter 2. In which case, you automatically get that the expected value of such a chi-squared random variable, of x is going to be, well, it's going to be nu over 2 divided by 2 times 2, which is going to be nu, and its variance is going to be 2 nu, because you're going to have nu divided by 2 times 2 squared, or 4, so nu divided by 2 times 4, which is 2 nu. Okay, so why do we care about this? Not so much for modeling real-world phenomena, because I can't imagine using a chi-square distribution to attempt to model a real-world phenomena when you could use the gamma distribution instead and have 2 parameters instead of 1. I would imagine that by doing that, you would be allowing yourself a more general fit and more like freedom in what distribution you're allowing. So I don't think that chi-square distributions are used so much to model real-world phenomena, but they're very important in statistics. They show up as the limiting distribution of certain statistics, or the actual distribution of certain statistics. So it's more important as a statistical distribution, as a distribution describing the behavior of certain statistics, rather than something that's modeling real-world behavior. But whatever, we will work with the chi-square distribution for now. There is a table for working with the chi-square distribution in Devore's book. It's table 8.7, which I'm not really going to mention here. In this class, we would only ever use R. So suppose that s squared follows a chi-square distribution with 9 degrees of freedom. Compute the expected value of s squared, the variance of s squared, and the probability that s squared is greater than 3.325. So the expected value of s squared is equal to 9. The variance of s squared is equal to 2 times 9, which is 18. And now we need the probability that s squared is greater than 3.325. And for that, we're just going to go ask R what it is. So the function that we're using is p chi squared, so p chi sq. So we're putting in 3.325. And the degrees of freedom parameter is df rather than nu. This is going to be 9. And then finally we want the upper tail, so we'd say lower tail equals false. So false. Oh, by the way, I think I should mention this. There's also these, we could have done alternatively f, and that does the same thing. So there's kind of this shorthand f and t for false and true. Don't use those. Please don't use those. The reason why you shouldn't use those is because I am allowed to change their value. Right? Or more maliciously. More maliciously. Like, we're going to say t is false. Yeah, it's not going to stop us, so we get this. That's not what we wanted. So do not do that. Do not use those things. R allows it, and they probably should just forbid it, because it's too easy to change. You are allowed to change those values, so you cannot count on what they're going to be in general. Right? Like, if you haven't said it in your session, then I guess you're okay, but it's just better to not do it. Okay, the probability that we got in the end was 0.95, I guess. So, and we can...
All right, so I finished the exponential and gamma random variables. I think I figured out why it wasn't included in the actual playlist. It's really similar to looking at like an exponential distribution. So like maybe not really worth making its own class, because like you end up using like, I think it's the same function even. Like even though it's a gamma function, and it's cool to see the gamma function introduced. Like it kind of seemed like the R code was almost exactly the same, just with a different parameter. So this last lecture, the exponential and gamma RV random variables, like all it was, so it was chapter 4, section 2, and it was like shockingly similar to things we've seen before. So yeah, it seemed a little bit like not the best use of time. So now that normal and exponential and gamma functions are done, that means I can now go to
sometimes
more random variables, which would be section 5 of chapter 4.
We are now going to start another section, this one with even more continuous random variables that often show up in applications and in various contexts. I mean, I would say that every one of them are pretty important. There's a lot of random variables, just in case you were wondering. Like, people have created random variables for many different situations. Some random variables are useful for describing real-world phenomena. That's what they're for. Other random variables are used for more of a statistical context, where you've got some test statistic and you're describing its distribution. So there's a lot of them, but we're just going to talk about a few more. The first one we're going to talk about is the Weibull distribution. This has a shape parameter alpha greater than 0 and a scale parameter beta greater than 0, which already makes it sound kind of like the gamma distribution that we talked about before, which also had a shape and scale parameter. And in fact, the Weibull and the gamma distributions are pretty similar. I mean, they are certainly not the same. They are not the same distribution. They are not the same random variables. They have certainly different properties. But at the same time, though, in modeling context, it's actually a good question whether some phenomena in question should be modeled using a Weibull or a gamma. So that's actually something, like, these are often pretty similar to each other in practice. All right, so here is the PDF of a Weibull distribution. So we have f of x alpha beta. Remember that this is the shape parameter, and this is the scale parameter. All right, and this is going to be, so our PDF is going to be alpha divided by beta to the power alpha, x alpha minus 1, which is making it look a little bit like the gamma. But then we have the e, which, all right, it's even looking even more like a gamma, but it's x divided by beta to the power alpha. And this is if x is greater than or equal to 0. It's going to be 0 otherwise. All right, okay. So the mean and variance in CDF of the Weibull distribution are given below. All right, so here is going to be our mean. The expected value of this random variable x is going to be
we're starting right away with an example of the Weibull distribution.
All right, so
which,
beta times
Curtis
gamma,
is pronouncing as Fable.
1 plus 1
it
over
looks like
alpha.
Wable.
So that's the expected value.
But I guess it is
and
German.
the variance
so it makes sense. It's, I guess,
of x.
Fable.
I'm going to want to zoom in for this.
But
So, let's see.
Curtis does have sometimes
So the variance
pronunciations of things that I don't
x
always
is
agree
beta
with.
squared.
He pronounced.
Then we've got
I thought it was Poisson.
Gamma 1
and he
plus
pronounces
2 over alpha
Poisson.
minus.
I'm gonna have to look that up later. This could be like a Dubois
1 over
thing
alpha,
where I always thought it was Dubois
squared.
and then found out it was
You
Dubois.
can pretty much see in the
Alright,
variance
going
formula
back to the lecture.
that the shortcut formula that I described before, it's definitely being used there. You can basically see it being used. And then we've got the CDF f of x. So f of x parameterized by alpha and beta. This is going to be, well, okay, this is going to be 0 if x is less than 0 naturally, and otherwise it's going to be 1 minus e to the power negative x over beta to the power alpha if x is greater than or equal to 0. And you know what? I'm going to go ahead and give you a percentile function. So a to p will be, let's see, well, this thing, these random variables are going to be at least 0. So we'll say 0 if p is equal to 0. And these random variables are unbounded, so we'll say infinity if p equals 1. Again, that's not a number, but but whatever, fine, it's not a number. We'll do it anyway. And otherwise, we have a to p. No. Why am I writing that again? Oh, that button's still not working. Okay. And then we've got a beta times negative log 1 minus p to the power 1 over alpha. All right. So there's our percentile function. So yeah, I mean it looks pretty similar to the gamma function in many ways, or the gamma distribution. Looking at this, I see similarities between the two, but they are not exactly the same. This has one nice feature that the gamma distribution didn't have, which is that the CDF, you don't have some weird-looking integral. You don't have some incomplete gamma function showing up. It's actually a very nice formula that's more elementary. The expected value and variance are not nearly as nice as they were in the gamma case. But whatever. What I remember this random variable being used for is I've seen it used for modeling hazard rate, more elementary. P equals 1. Again, that's not a number, but whatever, fine, it's not a number. We'll do it anyway. And otherwise, we have a to p. No. Why am I writing that again? Oh, my button's still not working. Okay. And then we've got a beta times negative log 1 minus p to the power 1 over alpha. All right. So there's our percentile function. So yeah, I mean it looks pretty similar to the gamma function in many ways, or the gamma distribution. Looking at this, I see similarities between the two, but they are not exactly the same. This has one nice feature that the gamma distribution didn't have, which is that the CDF, you don't have some weird-looking integral. You don't have some incomplete gamma function showing up. It's actually a very nice formula that's more elementary. The expected value and variance are not nearly as nice as they were in the gamma case. But whatever. What I remember this random variable being used for is I've seen it used for modeling hazard rates. Or a notion of hazard, like so let's take, for example, the exponential distribution, which, by the way, examine this very closely, and you can see that the exponential distribution is a special case of a Weibull distribution as well. So exponential is a special case of both gamma and Weibull. And you can see that if you take your shape parameter to be 1, you get an exponential random variable. because their PDFs are essentially the same, and their CDFs too. So you're going to get an exponential. Anyway, I remember reading an article in a magazine called Significance, which is a statistician's magazine, and they were discussing there how you can use the Vabel to model what's known as hazard or time until failure. You can think of the exponential distribution as modeling time until failure. It's just that when some object fails, right, which failure it can be thought of as time until failure can be thought of as time until an event happens. Okay. With the exponential distribution, what you're saying is that if this component hasn't failed by now, that doesn't really tell you much about when it's going to fail in the future. Like the odds of it. failing 5 days from now is the same as it was when you first got the component. So the hazard rate hasn't really changed over time. Whereas the Weibull distribution allows for you to consider different methods of methods of failure. Like, for example, you could have an aging component where as time goes on, the likelihood of failure increases. And I think, and this paper or article even mentioned something about what parameters can be associated with that. I think if you have larger shape parameters, you have a higher, you have basically this aging factor. Or potentially you could have a situation where components tend to fail early, and that means the hazard is more towards the beginning, and then after that, hazard has a tendency to decrease. So you can model many different types of hazard. The gamma distribution is also, in a way, able to model hazard, but it's going to view hazard very differently, where a series of steps are going to happen before failure happens. That's how I would see gamma understanding hazard. So that said, this one advantage of this Weibull distribution is that it's rather expressive, which you can tell by examining its PDF for different combinations of alpha and beta, and the gamma distribution does not have this level of expressiveness, I would say. So for instance, I'm going to create some sketches of what PDF it can, types of hazard, allows for you to consider different methods of methods of failure when you first got the component. So the hazard rate hasn't really changed. With the exponential distribution, what you're saying is that if this component hasn't failed by now, you can think of the exponential distribution as modeling time until failure. It's just that when some object fails, how you can use the Weibull to model what's known as hazard, or a hazard function, or like magazine. And they were discussing there how you can use the Weibull to model what's known as hazard, or a hazard function, or like time until failure. You can think of the exponential distribution as modeling time until failure. It's just that when some object fails, right, which failure it can be thought of as time until failure can be thought of as time until an event happens. Okay. With the exponential distribution, what you're saying is that if this component hasn't failed by now, that doesn't really tell you much about when it's going to fail in the future. Like, the odds of it failing 5 days from now is the same as it was when you first got the component. So the hazard rate hasn't really changed over time. Whereas the Weibull distribution allows for you to consider different methods of methods of failure. Like, for example, you could have an aging component where as time goes on, the likelihood of failure increases. And I think, and this paper or article even mentioned something about what parameters can be associated with that. I think if you have larger shape parameters, you have a higher, you have basically this aging factor. Or potentially you could have a situation where components tend to fail early, and that means the hazard is more towards the beginning, and then after that, hazard has a tendency to decrease. So you can model many different types of hazard. The gamma distribution is also, in a way, able to model hazard, but it's going to view hazard very differently, where a series of steps are going to happen before failure happens. That's how I would see gamma understanding hazard. So that said, this one advantage of this Weibull distribution is that it's rather expressive, which you can tell by examining its PDF for different combinations of alpha and beta, and the gamma distribution does not have this level of expressiveness, I would say. So for instance, I'm going to create some sketches of what PDFs of the Weibull distribution could look like. Here's x, here's f of x. If alpha equals 1, what we get is an exponential distribution. Okay, and if we have, say, alpha equals 2 and beta equals 2, a sketch of what this would look like is something like this. It kind of looks like a gamma distribution. And if we were to, say, have alpha equals 10 and beta equals 1, we have a very different looking shape where it increases quite rapidly up to a point, and then it has kind of this sharp drop, and then kind of continues on. So you can end up with a lot of different shapes for the PDF, which means it's a rather expressive random variable. Here's some R code creating some plots of the density function, which I would suggest that you play around with, just to get a sense of what you could possibly get with different combinations of alpha and beta. So this, by the way, is 0, because this thing's going to be from 0 on. All right. So let's see some examples. This is some unfortunate typesetting. Wind speed in meters per second at the site of a wind turbine is believed to follow a Weibull distribution with alpha equals 2 and beta equals 8. Compute the mean and median wind speed and the standard deviation of wind speed. All right, so we're going to have to take advantage of as much of this space as we can. So W, I hope I have the whole thing there. All right, so W is following a Weibull distribution with parameters 2 and 8. All right, so let's compute the expected value of this random variable. So expected value of w is going to be, according to our formula, 8 times the gamma function at 1 plus 1/2. So that's equal to 8 times gamma at 3/2. We don't know what it is. We don't know what the gamma function is at 3/2, but we can kind of reduce the argument in the gamma function and say this is 8, and then we've got 1/2 gamma 1/2, because that's one of the properties we have for the gamma function, which then reduces that to 4 gamma 1/2. And gamma at 1/2, well, actually, we know what that is. That's going to be the square root of pi. So in the end, we get that the expected value is going to be 4 times the square root of pi, which is approximately 12.5 meters per second. Okay, let's compute now the variance. Ooh, this is going to be not so fun. The variance of w is going to be, all right, according to that formula, we've got 8 squared, and then we've got inside gamma 1 plus 2 over 2, which is 1 plus 1, and then minus gamma at 1 plus 1/2 squared, which is going to be 8 squared. So gamma at 2 is going to be 1, and then we have minus gamma at 3/2 squared, all right, which is going to be 8 squared, and then 1 minus. So we've basically established up here before that gamma of 3/2 is a square root of pi over 2. So this will be pi over 4. Okay. All right, and we'll just kind of leave it like that, because now I want to compute the standard deviation of this random variable. So the standard deviation of w, take the square root of everything, and you're going to get 8 times the square root of 1 minus pi over 4. And I have no idea what that is. So off the top of my head, what that would be as a decimal number, but whatever. Okay, what else did they ask for? Or I asked for, because I wrote these. The median. Yeah, so we want the median too. All right, we will compute the median. So the median is going to be the 50th percentile, and that's going to be... So that's going to be, according to our formula, 8 times negative log of 1 minus 1/2 to the power 1 over alpha, which is 1 over 2. So this is going to be, after you do some work, 8 times the square root of log of 2. Yeah, and again, I have no idea what that's going to be. All right, so the turbine will not turn if wind speed is below 2 meters per second. Compute the probability that this occurs. All right, so the probability that the probability that the turbine doesn't turn. So the event that the turbine doesn't turn is the same as the event that the wind speed is less than or equal to 2. So 2 meters per second, which is going to be the CDF of the variable at 2 when its parameters are 2 and 8. All right, which is going to be 1 minus e to the power negative 2 over 8 squared. Which is equal to 1 minus e to the power negative 1/16, which is about 0.06. So there's a 6% chance that this turbine doesn't turn on any given day. All right, so here's some R code. We're working with the PDF d variable to understand the variable distribution, which is also specified by shape and scale parameters. How does that mean correspond with what I suggested? Oh, that's not quite the same. That's unfortunate. I think I might have miscalculated. Yeah, I mean, well, not on the R code. The R code's fine. My guess was wrong. So, oops. All right. The variance, I compute the variance and then compute the standard deviation by taking the square root of the variance. A lot of this stuff is stuff that you've seen before. All right. X is said to follow a log normal distribution. So we're now moving on to the next distribution, which is the log normal distribution. So X follows a log normal distribution. Denoted by X oops. All right. The variance, I compute the variance and then compute the standard deviation by taking the square root of the variance. A lot of this stuff is stuff that you've seen before. All right, X is said to follow a log normal distribution. So we're now moving on to the next distribution, which is the log normal distribution. So X follows a log normal distribution, denoted by X follows ln mu sigma if the natural log of X follows a normal distribution, or ln of X follows a normal distribution with mean parameter mu and standard deviation sigma. If this is the case, then the PDF of X will be so. F of X, parameterized by mu and sigma, is equal to 1 over the square root of 2 pi sigma x, and then we have e to the power, all this is going to be in this power, so I'm going to put a parenthesis around it, negative ln of x minus mu squared over 2 sigma squared. Okay, so to maybe just kind of reinforce the relationship. Oh, I should probably finish this and say that it's 0. Oh, so this is the case if x is greater than or equal to 0. It's 0 otherwise. All right. Anyway, moving on. If we say that y follows a normal distribution with mean mu and standard deviation sigma, then e to the power y follows a log normal distribution with parameters mu and sigma. That's a relationship between a normal and a log normal, and understanding that relationship is pretty important if you're going to work with these random variables. Okay, so we can express, in fact, the CDF of this random variable x like so. Here's its CDF. It's parameterized by mu and sigma. And this is going to be the probability that x is less than or equal to x, because that's what CDF means. But this is going to be equal to, as well, the probability that ln of x is less than or equal to ln of little x. Which, since ln of x is following a normal distribution, so since this part follows a normal distribution with mean mu and standard deviation sigma, we can then say that this is going to be the CDF of the standard normal curve evaluated at ln x minus mu divided by sigma. And this is going to be the case if our input x is greater than or equal to, well, okay, let's say strictly greater than, just so that we don't have to worry about taking the ln of 0. So if x is greater than 0, but it doesn't really matter all that much. And naturally, if x is less than or equal to 0, then we're going to say the CDF is going to be 0. Okay? Now, I wrote down mu and sigma, but this is one of those cases where mu is not the mean and sigma is not the standard deviation of this random variable. They're the mean and the standard deviation of the natural log of this random variable. The mean and variance of this random variable are going to be different. So we have instead that the expected value of x is equal to e to the power mu plus sigma squared over 2. That's the mean of this random variable. All right? And the variance of x is going to be e to the power 2 mu plus sigma squared. And all of that is going to be multiplied by e to the power sigma squared minus 1. Okay, that's the variance of x. So this random variable also has a fairly interesting PDF in that it can look like many different things depending on the configuration of mu and sigma. For example, here is what this PDF could look like if mu is equal to 1 and sigma is equal to 1. So this PDF would look kind of like so. So this is a right-skewed distribution, by the way, generally. With the Weibull distribution, over a certain range, it actually has it looks rather left-skewed. I should probably actually look at what its skew is. I think it's possible that I think even though it extends over infinity, is it possible for a random variable that has support from 0 to infinity to be left skewed? That's a good question. That's something that I should look into. But anyway, continuing on with what we were talking about. Another possible configuration, we can have mu equals 3 and sigma equals the square root of 3. Then we get something looking pretty different. We get more of a line as it decreases, rather than this sharp change in concavity early on. Or in the case of mu equals 3 and sigma equals 1, it looks like in a region the tail is actually rather heavy nearby. So, okay. All right. So moving on, here's some R code for working with this thing. The class of functions meant for working with log normals are L-norm functions. And I'm giving it the mu and sigma parameters, and you can see some plots of it. All right, so the next example, the current price of the stock with ticker symbol CGM is $26.18. The quants, so quants are it's a Wall Street term for, let's say, quantitative analysts, people who are using very mathematical approaches to understand the behavior of securities. So the quants believe that the price of the stock in a year is y, which is equal to 26.18 times x, where x is a random variable that follows a log normal distribution with mu parameter 0.1 and sigma parameter 0.2. Based on this information, find L and U such that the probability that L is less than or equal to y is less than or equal to U equals 0.95, and the probability that y is less than or equal to L is equal to 0.025. So basically, I want to find, what this says is that I have an equal-tailed region where the likelihood of the stock either being too low or too high is the same. And what I'm looking for are actually quantiles, such that in a year, the probability the stock is within that range is 0.95. So I'm actually looking for like a prediction interval. I believe with some level of confidence that the stock will be in this region in a year. That's basically what we're asking for. So what is this going to be? Well, we can start out by saying that the natural log of x follows a normal distribution with mean 0.1 and standard deviation 0.2. Okay. So, All right, let's start out by saying that the probability that the stock is within two. Okay, so ln of x minus 0.1 divided by 0.2, that it's within -2 and 2. So this is going to be about 0.95 by the 68, 95, 99.7 rule. So this random variable that I have in red, ln of x minus 0.1 divided by 0.2, that's going to be a standard normal random variable. So I'm saying that the probability that a standard normal random variable is within plus or minus 2, or plus or minus 2 standard deviations, is going to be about 0.95. And this is also equal to the probability, after we try to isolate ln of x so that it's by itself, this will be the probability that negative 0.3 is less than or equal to ln of x, which is less than or equal to 0.5. And this is basically looking at the probability that ln of x is within plus or minus 2 standard deviations of its mean. All right. So this is also equal to the probability that e to the power negative 0.3 is less than or equal to x, which is less than or equal to e to the power 0.5. And then we multiply everything by 26.18. So we say this is going to be the probability that 26.18 e to the negative 0.3 is less than or equal to 26.18 x, which is less than or equal to 26.18 e to the power 0.5. Okay, and then finally, recognizing that this part in the middle of the inequality, this part right here corresponds to y, which was the price of the stock. So we get to say that the probability that the price of the stock is between, after you also plug those other numbers into a calculator, 19.36 and 43.16. This is going to be approximately 0.95. Okay, so that means that this lower number corresponds to our answer L, and this upper number corresponds to our answer U. So those are going to be the lower and upper bound of our prediction of the stock. Okay, so actually some more terminology, some more background on this problem. It is actually common enough, let's say, or classical in a sense. A classical approach to modeling stock prices is to say that they're following some normal distribution. Now, we're going deeper than that, but actually, no, not a normal distribution, a log normal distribution. So that means that in classical financial models, such as the very famous Black-Scholes model, stock prices are understood to follow a log normal distribution. The random variable x, well, actually, ln of x can be understood as the return of a stock in a year in this situation. So x itself is just how much the stock increases or decreases, but as a multiplicative factor. Right. So 26.18 is just something we do to give the stock a starting price. So we're saying by how much. So x can be understood as the return of a stock in a year. And this modeling of stocks as following a log normal distribution, it's common in these classical financial models. It's also wrong. So so before you get too excited, just be aware of that. It is wrong. So anyway, here's some R code that's doing similar work. In this case, I'm just directly asking for this random variable x getting its lower and upper quantiles to then get the lower and upper bound of the price of the stock, which you get after multiplying by 26.18. All right, so our next random variable is a random variable following the beta distribution. So the beta distribution is, we've got in our book a beta distribution with 4 parameters, alpha, beta, A, and B. So now that said, I'm actually very familiar with seeing beta distribution with just 2 parameters, alpha and beta, but it's implicitly assumed that in that situation, A is equal to 0 and B equals 1, because the beta distribution is the distribution for a random variable that can possibly be between 2 numbers, so a lower bound and an upper bound. We have 2 shape parameters in this case. Excuse me. Alpha and beta are both shape parameters. So they're changing the shape of the distribution, whereas A and B, those are lower and upper bounds. So the probability that a beta random variable is below A or above B is 0. So in that sense, A and B are both location and scale parameters. And alpha and beta control the actual shape of the distribution. Okay, so the PDF of this beta random variable is going to be fx parameterized by alpha and beta, A and B, is going to be 1 over B minus A. And then we have, oh boy, I'm probably going to have to zoom in for this, because the formula in general is rather complicated. Okay, we got 1 over B minus A, and then we got gamma alpha plus beta divided by gamma alpha gamma beta. All right. And then we have x minus a over b minus a to the power alpha minus 1. And then b minus x over b minus a to the power beta minus 1. And this is going to be the case if a is less than or equal to x, which is less than or equal to b. And then this is 0 otherwise. All right, I'm not going to bother trying to write down any sort of CDF for this because that's just going to be a pain and not going to really be all that enlightening. The good news, though, is that if you choose alpha and beta to be integers, then what you actually have, then the interesting variable here is x. If you choose alpha and beta to be integers, then this is going to be a polynomial. So you're actually integrating a polynomial over some bounded region, and that's.
Okay, it is almost 5:30. I've been streaming for like an hour and 20 minutes. I forgot that I have a lot of cleaning to do before I can even cook dinner. So I think I will actually call it here for now, and then come back later, hopefully when my camera's actually working. Yeah, so I am minute 35 of the More RVs video, so covered kind of a lot. There's a lot of example writing right now, and it's covering, Curtis is covering the beta distribution. Yeah, so it's been, I guess, an interesting day today, covering a lot of different distributions. Hopefully we'll see more fairly soon. And yeah, if you are studying something and you want accountability, just send me a message. I'd love to hear what you're trying to work on. And I hope to see all of you either, like, I don't know, Kaggle, GitHub, something. Yeah. All right, my name's Aaron. I am your, I guess, friendly neighborhood government data scientist, and I am looking forward to chatting with you all later. Bye.